Welcome to AMAN-WATER, where every drop counts. Every day, you open the tap, the water flows, clean, clear, drinkable. But once it's been treated, what happens next? Where does it go? What path does it take? And most importantly, how does it reach your home? With the right pressure, at the right moment, without getting contaminated along the way? This journey, though essential, remains almost completely invisible, and yet it's a real technical feat.
I've taken that trip myself, from the top of the water tower all the way to your kitchen, and I can tell you, it's not just a simple pipe. Come on, I'll take you to see what happens after treatment.
In a previous video, we saw how raw water becomes drinking water, step by step, inside a treatment plant. But once it's ready to be consumed, it's still not at your home yet. The water leaving the treatment plant is not sent directly to houses, it's stored first. Why? For three main reasons. First, to maintain stable pressure throughout the network. Second, to keep an emergency reserve, useful in case of fire, a power outage, or sudden high demand. And finally, to handle peaks of consumption in the morning, in the evening, or during heat waves. You've probably seen some of these reservoirs by the roadside. When they're elevated, we call them water towers, but there are also underground or semi-buried ones, depending on the landscape and local needs.
From up here, I monitor the whole network. I'm the one who gives the pressure, but not too much.
These reservoirs are usually built on natural hills or on concrete towers, because the higher the water is stored, the stronger it flows down, and that force is what supplies the entire city. Once stored, the water must now reach every house, every building, every tap. To do that, it travels through a vast, buried network that we almost never see. First, there are main pipes, large conduits that carry big flows from the reservoir or the pumping station. Then come the secondary pipelines, which distribute water across neighborhoods, streets, and housing zones. Finally, the individual connections, smaller pipes that bring water directly to your home or apartment building. Not all these pipes are made of the same material. The choice depends on pressure, soil type, lifespan expectations, and of course, the budget. For example, ductile iron is very resistant, PVC is practical for small diameters, and HDPE, high-density polyethylene, is flexible and perfect for unstable ground.
Personally, I like HDPE. It bends, but it doesn't break.
To make sure water reaches every tap, even the farthest or highest ones, one thing is essential: pressure. Without pressure, water doesn't move, it stagnates. With too much pressure, the pipes get damaged.
It's like blowing through a straw. You need just the right amount, or it'll burst.
Gravity is the simplest and most sustainable method. You store water high up, and it flows down naturally. Booster stations, those are pumps, add extra force when gravity isn't enough, for instance, in flat areas or distant districts. Valves and regulators help fine-tune pressure, not too high, not too low.
When pressure gets too strong, I'm the one who takes the hit.
Too low, and the water won't reach upper floors. Too high, and it causes what we call water hammer, small shock waves in the pipes. That's bad for the network. We've seen that pressure is what pushes water to the tap. But to keep that pressure consistent all the way, you also need to choose the right pipe diameter. That's called pipe sizing. We start with flow rate. First step: estimate the water flow to be delivered. You calculate it by multiplying average water use per person by the number of inhabitants.
For a neighborhood of 800 residents, you get an average flow rate of about 0.015 cubic meters per second, if you assume 160 liters per person per day.
Next, choose an appropriate flow velocity. In drinking water networks, we aim for between 1 and 2 meters per second, a good balance between efficiency and wear. With flow rate and velocity, you can calculate the pipe cross-section, then its inner diameter.
For example, with a flow of 0.001 cubic meters per second and a velocity of 1.2 meters per second, you get an inner diameter of roughly 33 millimeters. Since that size doesn't exist, we select the next standard pipe size, 40 millimeters.
But beware of head losses. A properly sized pipe isn't just about flow rate. As water travels, it loses pressure due to friction along the walls. That's what we call head loss.
The longer or narrower the pipe, or the faster the flow, the more pressure you lose.
Head losses are a fascinating, though quite technical, subject. If you're interested, tell me in the comments. We could make a full video about it. Methods, charts, and real-world cases. One last calculation: the pressure at the outlet. Once the losses are known, you subtract them from the initial pressure and make sure at the end there's still at least 1 bar, which equals 10 meters of waterhead. Finally, you pick the nearest higher standard diameter. And that's it. A well-sized pipe means less waste, less wear, and optimal pressure.
Me, I work with 90, 110, 160 millimeters, but never at random.
The water leaving the treatment plant is drinkable, but just because it's clean doesn't mean it will stay clean. Between the reservoir and your tap, a lot can happen. So, how do we make sure the water keeps its quality throughout the network? First safeguard: residual chlorine. A small amount of chlorine is deliberately left in the water, just enough to prevent recontamination along the way.
You can't smell it, but it's there, and thanks to it, no microbes survive, even at the far end of the city.
Second factor: temperature. When water moves too slowly or stays too long in warm pipes, it becomes more vulnerable to bacteria.
In summer, it's not just ice cream that melts, the water in pipes heats up quickly too.
Third point: old pipes, sometimes made of lead or corroded metal, can release particles into the water.
Yuck. Even clean water can pick up impurities just from the pipes.
That's why, every day, technicians take water samples across the network. They measure chlorine, turbidity, temperature, making sure everything stays within standards.
Well-transported water is well-protected water.
Once the water reaches your street, it has one last step: getting into your home. It goes through what's called a service connection, a small pipe linking the public network to your private property, running under the sidewalk. Before it fully enters the building, it passes through a water meter. This little device records how much water you use. That number is what your bill is based on.
I love meters. They count every drop without complaining. But if yours spins at night, it might mean a hidden leak.
Up to this point, an entire chain of engineering has worked to bring clean water all the way to you. But from the meter onward, it's in your hands.
So drink it consciously. Each drop has traveled a long way.
And now, grab a glass of water and stay hydrated. If you're into this topic, don't forget to subscribe, hit the bell, and come with us to explore the world of water.